Hello, everyone. Thank you for coming today. Today we're going to be listening to Luca Mesiti speak about two-dimensional aspects of topos theory. Thank you.
Okay, I'm sharing my screen. Can you see it?
Yes.
Yeah, okay. So first of all, thank you very much for letting me speak here at this seminar. And today I'll talk to you a bit about my PhD thesis, where I contributed to expand the two-dimensional elementary topos theory, which is quite recently born, but I think very interesting, and also thinking about how useful is elementary topos theory in dimension 1. Maybe this is going to be very useful as well. In dimension 1, everything is quite well known now. And the archetypal elementary topos is the category set of sets and functions. And what is arguably the most important ingredient of an elementary topos is the subobject classifier. And here in this archetypal case, it's the inclusion of true in the set of two elements that we conceive as true and false. And this is universal in some sense, which is that every subset of this form can be encoded in a unique way with a map from X into this set of true and false, forming here a pullback. So that we have a function that takes maps into 2 and produces subsets of the domain of those functions by calculating pullback along this inclusion of true into true and false. And this is a bijection. And from this, we can extract a very important notion of subobject classifier. Classifier in a category C is a map that starts from the terminal object that we conceive as picking true inside an object of generalized true values, such that for every X in C, the map that takes maps from X to this omega, to the generalized true values, and produces subobjects of X. This is the bijection. So we extracted from this archetypal case this definition, and this is the most important ingredient of an elementary topos. On top of this, you just ask Cartesian closeness and to have finite limits. But this is maybe the most important piece. And in dimension 2, it's still not so clear what an elementary topos should be, an elementary 2 topos, but we are beginning to understand what should be a subobject classifier in dimension 2 at least, which is going to be the most important ingredient. So if we look at elementary 2 toposes, we have that the archetypal case is going to be cut, the 2 category of categories. And here we need to understand what is the right generalization of subobject classifier. And Mark Weber had the following idea. First of all, we need to understand what we want to classify. And in dimension 1, we classify subsets here in the archetypal example. And subsets are functions whose fibers are either singleton or empty sets, depending on whether the element on which you take the fiber is in A or not in A. And Mark Weber thought that then in dimension 2, we want to increase by 1 the dimension of these fibers in the morphisms that we want to classify. And so we should classify maps whose fibers are general sets. And this is an idea which is very close to homotopy theory or homotopy type theory. So we want to classify maps whose fibers are general sets. And the perfect notion that gives these are discrete op fibrations with small fibers. Now, you don't really know how much do you know about discrete op vibrations. Maybe I'll say a little thing. But first of all, we have a classification of these discrete op vibrations in CAT, which is given by the category of elements construction or Grothendieck construction. And these are the same thing as presheaves from B to Z. And it's still true that this classification can be recovered as some kind of limit along the inclusion of something true inside the generalized object of truth values. So the inclusion of the singleton into set. And the right limit to consider here is the comma object rather than the pullback, which is like a two-dimensional version of pullback in which rather than having a universal commutative square, we have a universal square field with a two-cell inside. And so what we have is a functor that takes copresheave and produces discrete op vibrations with small fibers over B. And this is given by taking comma objects along this inclusion. Or equivalently, this is the category of elements construction or Grothendieck construction. And this is an equivalence of categories. Now, if you don't know what a discrete op vibration is, well, it's just a reorganization of the data of a copresheave of a functor into set. But you can also say that it's a functor such that for every object E above and for every map of this kind in the category below in B, there exists, call it F, there exists a unique lifting F bar into B. So we can uniquely lift all these morphisms below to every object we take above. And this actually only gives you a discrete op vibration. Then small fibers mean that the fibers of this functor are going to be set. So it's just a size issue, basically. And the category of, category of elements construction takes a copresheave, views it as a collection of sets, and tries to glue them together by making all of these starting sets to be the fibers of a functor into B. And on the other direction, this is an equivalence of category. We start from a discrete op vibration, we consider the fibers, and we send each object B of B to the set given by the fiber over that object. And so from this, we can extract a definition of subobject classifier in dimension 2. So now we take L, a 2 category, and we say that a good 2 classifier is because this is a definition I propose in my thesis, which is a bit stronger than Mark Webber's definition. This is because I call it good. And is still a map of this kind, so the inclusion of something true into a generalized object of true values in L, such that for every object F in L, the functor that takes maps into omega and produces discrete of vibrations over F, calculating comma objects along omega, is an equivalence of categories. At least, maybe it's better to say forms an equivalence of categories. When we restrict the codomain to the discrete of vibrations over F that satisfy a fixed pullback property P. So actually, this is dependent on a fixed pullback property P for discrete of vibrations. That in this example, this is going to be having small fibers. Actually, in all examples of this code, P is going to be having small fibers, but it could be something else, principle. So discrete of vibrations satisfying P. And this is with respect to P. And so what a problem that we have with this definition, it nicely generalizes what we have in dimension 1, but the problem is that it's quite hard to prove that something is a good to classify. Because for every object of our 2 category, we need to prove equivalences of categories. And for example, also that the category of elements exhibits equivalences of categories is not so immediate. And this is also the archetypal example. And so what I proved in my thesis is that we can reduce the study of a good to classifier to dense generators. And I'm first going to recall what a dense generator is. So a 2 functor I from Y to L, we take it fully faithful. So we are basically selecting a family of objects of L. We take Y small. This is dense if the associated functor from L to Y of cat that restricts the Yoneda embedding. So the Yoneda embedding would send an object L to this thing, this representable over L. And here we restrict this Yoneda embedding to only look it from the eyes of this Y. So in this way. And we ask this to be fully faithful. So what's the idea? The idea is that the Yoneda embedding is always fully faithful. And this means that all the information of an object L, of every object, can actually be given by looking at all the maps into L. This is maybe one of the starting ideas of category theory. All the information on an object is given by all the relations that this object has with all the rest of the category. And what this definition of dense generator means is that it's actually enough to look at L from the eyes of this small family of objects of L. So you don't need to look at the relations with the entire category. You can just look at the relations with this family of objects, and this is enough. And we have nice equivalent characterizations, which is that every object F in L is I absolute colimit. I absolute means nice. It means preserved by this I tilde, but you can read it as a nice colimit of a diagram which factors through y. So basically, to build any object in your 2 category, you just need these objects in the full subcategory y. And then you can build everything else via nice colimits. And I prove this theorem, which says start with I from y to L, a dense generator. And from something that you want to prove that is a good 2 classifier, so omega in L from the terminal, then the following are equivalent. 1, omega is a good 2 classifier, which means that for every f in L, the functor at f is an equivalence categories. And 2, just for every y in Y, the functor at Y is an equivalence. And actually we need a bit more, which is that an operation of normalization is possible. And now to understand a bit more this theorem, we can look at, we can draw a picture that explains a bit what happens here. Let's focus on the essential subjectivity. So we start from a discrete of vibration that satisfies the property P, something that we want to classify. And dense generators tells us that we can build this object F as a nice colimit of the dense generators. And so we can consider the cocoon of this colimit. And we can consider then the change of base of this starting phi along the cocoon that represents the colimit. And now we have this bunch of discrete up vibrations over the dense generator that by assumption, this by 2, we can classify. So we can find these characteristic morphisms into omega that recover these discrete up vibrations over the representables. And then the idea is that we want to induce a morphism here on the colimit F that builds phi, which means that the comma object gives this phi. And well, this is possible, at least if these characteristic morphisms key CX form a cocoon, and this is precisely what the operation of normalization is about. And there is something a bit tricky here, which is that we are in dimension 2, and so we need 2-dimensional colimits. And you probably know that in dimension 2, conical colimits are not sufficient anymore. We need weighted colimits. But here, actually, we need the following. We need that in dimension 1, it's always true that a colimit in a slice category is given by taking the colimit of the domains of the diagram and then inducing the map via the universal property. So colimits in slices are all of this kind. And we have this property that's starting from a Q, from the colimit in our category. We can build this as a colimit of something in the slice. And in dimension 2, what I proved in the thesis is that this is still true, but rather than using weighted colimits, which are bad on the right-hand side, because the right-hand side is still conical in shape, we need to consider an alternative of weighted colimits. which is given by a form of marked Hoplux colimits. Now, it's not really important for this talk, just to tell you that you cannot really use weighted colimits for this because you want this property, and this is only realized with an alternative of weighted colimits. And to give you an idea of what this alternative of weighted colimits is about, we can say the following. In dimension 2, conical colimits are not sufficient anymore, because if you want to understand all the data of a category C, then functors of this form from the terminal into C are not sufficient anymore. And because they are only going to give you the objects. And so you have two ways. So these don't suffice. And you have a first solution is considering maps from everything. So from, I don't know, W to C, from everything, or even only from 2, which is going to give you the arrows of this category. Or second solution, you can still consider these functors from the terminal, but also now natural transformations. And this is going to give you all the data of C. And the left-hand side corresponds to weighted colimits. The right-hand side corresponds to this alternative. So you keep cocoons, but you are now given 2 cells inside to handle. And now I want to show you an example that shows the benefit of this theorem. So let's look at the archetypal example of cat. And we want to prove, but in a faster way, that the inclusion of the singleton into set is a good to classify. And here we have that the singleton category is dense in cat, just the singleton category alone. And so it suffices to consider, let's call it omega. So suffices to consider the functor set 1. And this, what does it do? It takes a functor from 1 into set and sends it to discrete of vibration with small fiber over 1. But this is just a set, because fiber over 1 means nothing. And so this functor is actually taking a functor from 1 into set and sending it to the image of the unique element of this one. So it's doing nothing. And this is clearly an equivalence of categories, probably also an isomorphism. And so we immediately get that the category of elements construction is fully faithful and classifies precisely all discrete of vibrations with small fibers. And moreover, the proof of the theorem above is constructive. So we also have a recipe. We start from a discrete of vibration with small fibers. We can build B as a colimit of the dense generators. And the cocoon just looks at the objects B of B. We consider the change of phase of P along this, which gives us the fibers. And then we classify this. But the classification is trivial. We just consider these fibers, and then we collect them together. And this is precisely what we know of the Grothendieck construction of the category of elements, that from a discrete of vibration, we can produce a copresheaf by collecting the fibers together. But all of this is given just by the trivial observation that over 1 everything works, and this is trivial because this functor is doing basically nothing. And then there is another context in which this theorem has great benefits, which is the context of stacks. And luckily for me, Elena last week introduced stacks. Maybe just a quick recall. So we have functors into cat, two functors. I'm going to take them strict to functor. And this is a stack. If we can glue together compatible local data. So a stack is a two-dimensional generalization of a sheaf. And what happens is that we want for every C and for every S a covering of C. You can think of this as an open covering of the object C. So a collection of parts of C that build the entirety of C. We want that we can glue these collections of local data. So for every F in the C, which you can think as an open covering, we have an object over D, which means a local data at D. And we want to be able to glue all of these together in a unique, in an element, a global element in F of C, such that for every F in S, we can recover all the starting local data. And actually, this would be just a sheaf. You need to ask a compatibility. For sheaves, we ask this, such that given G and then F, we want that the descent along G, so going into a more local path from the data on F, this is equal to the local data directly in D prime. And this would give you a sheaf. What we are asking here is a weakening of this. So we actually take isomorphisms here, phi fg, and we want to glue these local data together in an equally weak way. So we will have an isomorphism psi of this form, psi-f. So we can still glue compatible local data, but which are compatible only up to isomorphisms, into a global element that is going to recover all the local data up to isomorphism as well. And this is a stack. Probably Elena did better job than me last week. But why are stacks useful for us? Because exactly as sheaves give us the archetypal example, not the archetypal maybe, but a prominent example of Grothendieck toposes. Actually, every Grothendieck topos is basically a category of sheaves. We will have that in dimension 2. Every two-dimensional Grothendieck topos is basically a two-category of stacks. So these stacks give two-dimensional Grothendieck topoi or toposes. And there is a fundamental theorem in dimension 1, which says that every Grothendieck topos is an elementary topos. And here we want to find the two-dimensional generalization of this. So we are going to look at the case of stacks, which give us two-dimensional Grothendieck topoi, and find a good two classifier in them. And then if we do this, we can, for example, study more the two categories of stacks to understand which other properties we should ask an elementary two topos. So we can, actually it's very important to look at these two categories of stacks to understand elementary topos theory in dimension 2, which is just at the beginning. There's a lot to do. And so first, let's start with just two presheaves into cat. These are going to be, for example, stacks with respect to the trivial topology. But anyway, every stack can be embedded in here. So let's start with this. And here we have that representables form a dense generator. You probably know that every representable is a nice colimit of, every presheaf is a nice colimit of representables. The same happens in dimension 2, and it's what is exhibiting this as a dense generator. And so this means that we can just look at the functors over the representables, and these are of this form. Take maps from the representables to omega and sends them to discrete op fibration with small fibers over the representables. And we want these to be an equivalence of categories. But the Yoneda lemma says that the left-hand side is omega of C. And so Yoneda lemma is telling us how we need to define up to equivalence a good classifier in two presheaves. Tells us that up to equivalence, we have to send C to discrete op fibrations with small fibers over the representable. And actually, this doesn't fully work because this only gives you a pseudo functor. So it's not a strict functor into K. It's not even clear that this is a small category so that it belongs to K, but there is the indexed Grothendieck construction that comes in help. This is joint work of me with Elena Caviglia, which is last week's speaker. And it tells us that we can equivalently consider presheaves on slices. And actually what Elena and I proved is that in general, op fibrations in co-presheaves over some F are the same thing as co-presheaves on the Grothendieck construction of F. So this is an index version of the Grothendieck construction. Basically, an op fibration in co-presheaves is on every component an op fibration. So it's a collection of op fibrations. We can apply the Grothendieck construction to each of them and get a bunch of functors into cat, and we can collect them together into a functor that starts from the Grothendieck construction of the base. And this is what we prove. And this works because let's call it omega tilde that sends C to these presheaves on slices is a good true classifier in two-dimensional presheaves. I've not told you what the true is inside of this. Omega tilde from 1 to this picks the constant at 1 functor on every component. And now we want to understand the case of stacks. So we have started with two-dimensional presheaves with C op cat. Now we want to restrict omega tilde to a good two classifier omega j in stacks. So these are stacks. And what do I mean by restrict? Means we have an inclusion of stacks inside two-dimensional presheaves. And we have a good two classifier here. We want to restrict it to a good two classifier in stacks, which means finding some stack omega j, which is included into omega tilde with the map which is injective on objects and fully faithful by representability. So this is also called the chronic arrow. It's just an embedding, where at least if we consider not omega j, but its inclusion into two-dimensional presheaves, in a way that also factors this map from the terminal into omega tilde through omega j. And then we want one more thing of this omega j. We want that every time we start from this phi, the discrete of vibration with small fibers in stacks, what we can consider the underlying thing in two-dimensional presheaves. We can certainly classify this because we have a good two classifier in presheaves, and so obtain these characteristic morphisms key. And we want that all these characteristic morphisms factor through omega j. Key j. And what I proved is that if this factorization condition holds, this gives us the right characteristic morphism, and we have that omega j is a good to classify. Actually, we proved this more in general, that this way allows you to restrict good to classifier along nice full subcategories of something in which you have a good to classify. And at this point, it was just a matter of finding the right stack omega j to make all of this work. And the solution is the following. We want to restrict the good to classifier into dimensional presheaves, so that consider these presheaves on slices. We want these, we want to select some of these presheaves that behave well with the Grothendieck topology that we have. And so we just take sheaves on these slices. And this works. This is the good to classifier in stacks, which is important because now we know a generalization to dimension 2 of the fundamental fact that a Grothendieck topos is an elementary topos. Now we know that two-dimensional Grothendieck topos have at least a good to classifier, and then we can study them to understand which other properties to ask an elementary topos, for example. And this result also solves a problem posed by Hoffman and Stryker. They tried to do a similar thing, lifting Grothendieck universes to presheaves and sheaves. And with presheaves, they managed to, but then with sheaves, they tried to do this. And this didn't work for them because it's not a sheaf, but it is a two-dimensional version of a sheaf. It's a stack. And what we proved is that it's a stack, and it's a good to classify in stacks. And that's all for today. Thank you.
Anybody have any questions?
I guess I just have a question about this role of the smallest condition.
Okay.
Is this like an additional piece of data that you add to the category? Like what counts as small, or how exactly does it work?
Say it again.
So so you take these, you say classifies these small discrete vibrations, or the ones with small fibers, right?
Yes.
So is this notion of what counts as small, is this something you put in by hand? You say, I'm going to consider these things as small. So it's like, so an elementary two topos is a pair of a kind of two category and something which counts as what is small, or do you derive what counts as small?
So you need to start from a chain of Grothendieck universes, actually, because you want set to belong to cat. So you need to take set with respect to a fixed Grothendieck universe, which is going to tell you what is the smallest possible thing. And we want these fibers to be that small because the category of elements wants to consider, wants these fibers of this functor to correspond with the images of these presheaves inside of set. So you want the objects of set to be, you want these images to be small enough to be elements of this set, and so you want the fibers that correspond to them should be that small. And then you want...
But then in the general case, in like the definition of an elementary two topos, what plays the role of smallness there?
Well, that's why I took this property P, because maybe having small fibers doesn't make any sense in some more general situations. Then for stacks, for example, you can define what having small fibers is, because you have just on every component, you have op vibrations, and you can ask all of these components to have small fibers.
So is the property P like an additional like piece of information you have when you're saying something's going to be an elementary two topos? It's not just a category, it's a category plus the choice of this property P.
Yes, exactly. Because if you want to say that all discrete op vibrations of a certain kind are classified, you need this property P to be there. For example, Mark Webber actually only considers fully faithfulness of these functors. So he focuses on asking the classification process to be nice enough, but he doesn't focus on what gets classified, on the essential image of these functors. And what happens in the archetypal case of cat is that, well, all discrete op vibration with small fibers are precisely what gets classified. And in stacks, we have again something like this, that all discrete op vibration with small fibers are classified by these good to classify.
So are there any axioms on this property that you have, or?
It needs to be pullback stable for sure, because you want to do arguments like this one in the theorem. You start from a discrete op vibration that satisfies P. You want to consider this change of basis, and you want these ones to satisfy P as well. And then I also needed them to be stable per isomorphisms. So if a discrete op vibration satisfies P and you have something which is isomorphic to it, you want that as well to satisfy P. But nothing else than this.
Is it possible to like take this class P to be like really restrictive? Like, for example, just subterminals or something, and you recover something like a subobject classifier?
So you
like, is it possible to have this condition be like very restrictive, so it actually just corresponds to subobjects, like the usual definition of a subobject classifier?
I see. I haven't thought about it, but you're not ending up with something maybe that makes a lot of sense even in this archetypal case of cat. I don't know, the classification of subobjects in cat is not working so well. What works better is a classification of discrete op vibrations with small fibers.
Yeah, I guess it would be like it would still be a certain class of discrete up vibrations, but it'd be the class of discrete up vibrations whose fibers are subterminals.
I see. Yeah, it seems very interesting. I've not considered it.
Okay. Okay, thanks.
Could I ask a few questions?
Yes.
So, have you looked at possible examples in the case when the two category is poset enriched category, and specifically, what happens if we take the category of posets?
I see. I've thought a bit about it, but I suspect that that category, that two category, would have more of an enriched version of classifier rather than a two classifier. Maybe
So you think that this, so if B is a poset, I see. So you're saying that this definition will not give anything there, that there will not be anything.
No, I don't know. I've not thought so much about what this definition would give there. I just suspect that what works best in that example is an enriched version of classifier, which is something I've been thinking for a while, and maybe in future work
So I'm more asking not to find what is best for posets, but to kind of explore what your condition gives.
I see. I haven't tried up to now. I haven't tried.
Now the other question might be even crazier. What about if we take the category of monoids? Can some of this somehow reflect on? So posets, and for me, posets and monoids are two kind of subcategories of the opposite type of subcategories of the category of categories.
Yes. Yeah, for example, in dimension 1, I think monoids doesn't work so well, but maybe in dimension 2 they do, I don't know.
For monoids, I don't even know what will be the analog of set.
I mean just, yeah. I was saying just monoids in set, just don't work so well. I think they don't give you an elementary topos, for example, in dimension 1.
No, they don't. Wait, sorry.
But maybe
do,
the
right?
reason is that they work better in dimension 2, that I don't know. There's still a lot of things to explore. It's just recently born theory up to now.
Yeah.
There are also other two categories that one can try, for example, internal categories to a topos, for example. Maybe it's going to give you an elementary to topos as well.
Yeah.
Yeah, I don't know. I haven't tried so much up to now. I just focused on stacks because they are two-dimensional Grothendieck topoi, so they should definitely be examples of the theory. But there are definitely a lot of examples to try then that might be elementary to toposes as well.
I also have a slightly more general question, which also kind of related to Elena's talk, I think. So after Elena's talk, Hideo and I, we came across, Hideo is one of the students, he's I think in the audience. We came across torsors. Do torsors arise in either your work or Elena's work?
Yeah, more in Elena's work, probably.
Yeah, they are, it depends on the definition you found, but they are basically the same thing as principal bundles.
Aha, okay.
So, yes.
Great.
So yes, Elena's example of her talk on principal bundles corresponds to torsors, probably.
No more questions from my side. Thank you.
You're welcome.
Okay, if that's everyone, then thanks again for giving the talk. It was very interesting.
I'm glad to hear.